Welcome. In this video, I am going to discuss about magnetic torque. Before watching this video, I believe you know what is magnetic force. Any closed circuit carrying direct current will always experience a vector force, and the total vector force experienced by any closed circuit is zero in a magnetic field, basically uniform magnetic field. But it was found that even though the force is zero, torque is not generally zero. So when we are dealing with magnetic field and especially time varying magnetic field, it is necessary to define magnetic torque. So magnetic torque is also known as moment of force. When we are trying to define the torque or write torque equation, it may be necessary to consider the points where the torque is to be calculated and where the force will act. That is, there will be 2 points. A point at which I am going to calculate the torque, and there will be another point which will be at some distance where the force will be acting. If this is the scenario, then we are going to get the torque. So basically torque is defined as vector product of moment arm and force. So moment arm is usually notated by a vector r, and as you know, the force is denoted by F. So if you find the cross product of these two parameters, you are going to get what is magnetic torque. So this is how we mathematically calculate torque. So it's necessary to get an idea of what is this r vector before we proceed with the topic. So if I consider a three-dimensional coordinate system, it can be any coordinate system. Okay, so I am considering a three-dimensional coordinate system, and I have a force acting somewhere here, maybe. Okay, a force acting somewhere here at this point, so that the force is acting in some direction. You know that the force will have some direction. So from this point, okay, the force is acting in some direction like this. So this is my F vector acting at this point. Then if I am interested in calculating the torque at the origin, this is the origin of this coordinate system, if I am interested in calculating the torque, so I was initially talking about 2 points, right? So one point is this is the point where I am interested to know what is the torque, and this is the point at where my force is acting. So the distance between the point at which I am calculating the torque and the point at which the force is acting, so I can easily calculate that distance. Okay, a straight line distance, and this distance is nothing but it's a vector. So this distance is nothing but my moment arm, which is nothing but r vector. So if this is my r vector, this is my f vector, then cross product of these two vectors will give me torque. And going with basic definition of cross product, so when I have r and f lying on the same plane, whichever the plane this is, it is lying on the same plane, my resultant vector, that is t, if I cross these two, my resultant vector t is going to be in perpendicular direction, that is right angle to both r and f. So this will be my direction of torque. So I hope this representation is very clear. It's also necessary to know the unit of the torque. So unit of the torque will be Newton meter. It's very easy because force is measured in Newton and this distance will be measured in meter considering SI unit. So the unit of torque will be Newton meter. Okay. So to illustrate further, I can say that this R is moment arm and this is the force acting. So what will happen here basically? So when you have something, okay, this is a point where this moment arm is fixed. Just assume that it's fixed at this particular point. If it is fixed at the origin, okay, this particular arm is fixed at this origin and you are applying a force at the tip of this element. So what will happen when you apply the force? This is fixed, so it cannot go with the force or release and go with the force. So since it is fixed here, this will go into a rotatory motion. Is it not? Hoping that this force will act at every point. Or if this force is good enough, a single force, if I do this, since this is fixed here, it will rotate. Okay, so this is basically, this force can rotate this moment arm at its origin. So this is the idea of rotatory motion as well. This is used in machineries, electric machineries. Okay, going further, what if, okay, my viewers used to ask me, what if there are more than one force which are applied at different points? Then does this torque still exist, or is it impossible to calculate what is the torque if there are more than one points? That is the question. Like I have already one point here, I'll be using the same figure, okay, it will be more clear. So there is already a point here, right? I already have a point here. Let me name that point now. So this point, okay, maybe A1, or let me take it as A2. I have another point A2. Somewhere here I have another point A1. So I have a force acting at this point A2 as F2, and I have another force acting at the point A1. And to complicate things, what if this force is acting exactly opposite to my initial force F2? Okay, don't worry about the suffix because I am talking about F2 initially. Okay, doesn't matter. So I have a force here which is acting at point A2. I have another force acting at a point A1, which is some distance between them. There is some distance between them. And obviously this is at some distance from the origin, so I am going to have maybe another moment arm. Okay, so this moment arm I'll call now as R2 because it is corresponding to F2. So obviously I will have another moment arm here to A1, and this moment arm I'll call it as R1. Now the question is whether these two forces, that is F1 and F2, will act independently or whether there is any dependency. So in this case, why we are considering this is, my interest is, the beginning of this discussion we have told that in any closed current carrying circuit the total vector force will be 0. So this is just an example of that. Even though this is not a closed circuit, I am considering a force acting at some point A2, I am considering another force acting at a point A1, and they are equal and opposite. That means the resultant force is going to be 0. So my question now is, if the resultant force is going to be 0, whether the torque will also be 0. So this is asked in the other way. What if there are more points in the system where different forces are acting in different directions? Then whether still I will have the torque, or whether these forces will cancel each other, and whether the torque will go non-existence, or these forces may or may not cancel each other. In such cases also whether I'll get the torque. So these are the questions which you should be able to answer after knowing what is magnetic torque. So that is the point of discussion. So here I am considering 2 points where 2 forces will act such that these forces will become 0. So I am considering a system where the net force is 0. So okay, now net force is 0. So let me try to calculate whether this system gives me any torque. So we already know that F2 is equal to minus F1. There is no doubt because they are equal and opposite. Okay, now see, I have, okay, looking at this physically, I may have 2 torques. One torque is acting at the origin, which is due to the momentum R1 and momentum F1. Is it not? By going by the definition, I know that T1 can be written as, I'm not very sure, but I'm just writing it. Okay, T1 can be written as R1 cross F1 because this is just for definition. We have just defined it, torque. And similarly, I can write T2. If there exists a T2, then T2 will be R2 cross F2. There is no doubt in this. No doubt in this. Right? Then see, what I am going to assume is, if there is a torque, then it will be a total torque acting at the origin in the same direction, because this is also in the same plane, this is also in the same plane. So the resultant, as per the vector cross product vector rule, the resultant vector T1 and T2 should be perpendicular or normal to this plane containing R1 and F1 or R2 and F2. So keeping in that mind, T1 also will be perpendicular, T2 also should be perpendicular, and origin is my point. So there is no other way. My T1 also should be in this direction, T2 also should be in this direction, going with the conventional law, right? T cannot be bottom, T has to be in this direction. Agree? That means what? T is going to add it up. T is in the same direction, T is not going to cancel each other, T is going to add it up. Agree? So I will still get a T, but that T will be now addition of these 2 T's. They'll add up together to form my total torque. That means I have to add R1 cross F1 with R2 cross F2, and I'll be using this result because initially I assumed that forces are equal and opposite. So I can either substitute F1 as minus F2 or F2 as minus F1. So this equation becomes R1 cross F1 plus R2 cross minus F1, because F2 is minus F1. So this tells me that this equation can be written as T vector equals, F1 is common, this minus comes here, so this becomes R1 minus R2 cross F1, R1 minus R2 cross F1. This is nice. So I can calculate the total torque, okay, if there are 2 points like R1 minus R2 cross F1. Now what is this R1 minus R2? A basic rule of vector, right? R1 is the distance from this to here, R2 is the distance, means R1 is momentum of the first point force, R2 is the momentum of the second force. So basically this R1 minus R2 is nothing but R21, right? So R1 minus R2, vector R1 minus vector R2 is nothing but R21. With this we know R1 vector minus R2 vector can be written as R21 vector, distance formula, okay, R21 vector. So what would be that R21 vector? R21 vector will be a vector which is directing from point 2 to point 1. Agree? This is interesting. See, R2 vector is a vector which will be pointing from point 2 to point 1. So R2 vector is this, correct? So this is my R21 vector, right? So this equation can be further written as my torque is equal to R21 vector cross F1 vector. So this is my total torque. Okay, if I consider 2 points where 2 forces are acting, R21 cross F1. Now what does this infer? So when there are 2 points A1 and A2 at which there are 2 forces acting which are equivalent opposite, my torque does not depend upon individual moment arms. It is not going to depend upon how far I am measuring the torque. This is interesting. It just depends upon how far these 2 points are located. Is it not? Because this final equation has just R21 cross F1. R21 is nothing but the distance between points A1 and A2, and now it is independent of the distance from the origin where I am measuring the torque. So when the total force is 0, the torque is independent of choice of the origin or choice of the measurement point. So this is very important inference what we get from this discussion. I hope magnetic torque is clear, and when the total force when I say more than one force acting at different points and the total force is 0, still torque can exist, and this existing torque is independent of the choice of the point at which you are measuring that torque. Really interesting. So thank you for watching this video.